Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying AOD lecture 4. So basically we'll be talking about local and global minima maxima and ways to calculate them. So let us begin with the lecture. Let's first talk about local minima and maxima. So let's say we have a graph of, let's say this sort. So we can see these peaks and troughs over here. So these are nothing but local minima and maxima. So this point and this point is local maxima and this point and this point is local minima. Let's try to define them mathematically. Let's say this is point A and this is point B. So over here we have A plus H and A minus H. This is B plus H and B minus H. So in case of a local maxima, A should be greater than A plus H and A should also be greater than A minus H. But in case of a local minima, it is obvious that B should be lesser than B plus H and B should also be lesser than B minus H. That is how we define the basic definition of local minima and maxima, right? Now, what do we observe over here? We can see that there can be multiple local minimas and local maximas in a particular graph or function. So basically, it's not like we have just one local minima or one local maxima. We can have multiple local minimas and maximas. All we want is this particular condition to be satisfied at a particular point. Then we can define it as a local minima or maxima, right? Now let's talk about global minima and global maxima. Let's say we have a curve like that. I can clearly see that these 2 points are local maxima and these 2 points are local minima. But again, since we have defined a function from, let's say this point is A and this particular point is B, I can clearly see that the global minima over here is this particular point and global maxima is this particular point. So regardless how many local minimas and local maximas we have in the function, we can still have a different global maxima and global minima. But let's say if this was the case for a particular function, in that case this particular local maxima is also the global maxima. So either this can be the case, or this can be the case, both of them. So in case of local minima, we have just one condition that we have to check the vicinities. But in case of global maximas and global minimas, we have to check the endpoints as well, because we might have concluded that okay, this is the global maxima, but we haven't checked this particular point yet. So once we are done with the local minima properties, we have to check the endpoints as well to conclude for the global maxima and global minima, right? Now let's try to define stationary and critical points. So basically, stationary point means f dash equals to 0. If any function is there and we have to find out the stationary points, we have to do just the f dash equals to 0, and we can then find out the points where this particular equation holds. And for critical points, f dash equals to 0 or the function is non-differentiable at certain points. So why are we calculating these points? Because let's say we have a function over here. We have a function like this. I can see that this particular point is smooth, but this is, edgy. It's not having smooth corners, but it's having sharp corners. So it's non-differentiable over here, but still a local minima. It is also a local minima. It is also a local minima. It is also a local maxima. It is also a local maxima. So basically, at this particular point, it's non-differentiable. It's over here, it's differentiable. So with the help of critical points, we can find out the points where the function is turning. So basically, we can identify the points where there can be a probable local minima or local maxima, right? So that's why we have to calculate the critical points. So with that, let's discuss first order derivative test for local maxima minima for derivable functions. So this we were talking about critical points. We were talking about for all sorts of functions. So we'll be calculating f dash x equals to 0, and we'll also be calculating non-differentiability at particular points, and then we'll be checking the condition if this particular condition is being satisfied or not. And after that, we'll be talking about the edge points. So after doing all these things, we can conclude for any function local minima, local maxima, global minima, and global maxima, right? But this first order derivative test we are doing just for derivable functions. So what would be the first case over here? So before talking about the first case, in case of derivable functions, stationary points and critical points would be same, right? Stationary points would be same as critical points because there is no indifferentiability. So there is no point which is not differentiable. So that's why stationary points is same as critical points in case of derivable functions. Now let's talk about the case one. So let's say we have a function fx over here, and we found out f dash x equals to 0, and we got x equals to a as a point where this particular f dash x equals to 0 is happening, right? So basically that is our stationary or critical point. Now let's try to plot it. So the case one says this is point A, and on the left hand side we have positive value, and on the right hand side we have the negative value. So what is happening over here? So basically when we have a positive value of derivative, basically slope is going up. At x equals to A, slope is becoming 0, and on the right hand side of A, slope is becoming negative. So basically we have a local maxima over here. When this is the condition, when on the left hand side we have a positive derivative, and on the right hand side we have a negative derivative around a point where f dash x equals to 0, then we have a case of local maxima. Now case 2 is very obvious. Let's say we again have a function fx. We found out f dash x equals to 0 for x equals to, let's say, b. In that case, this is b, this is negative, this is positive. So basically slope is negative, it's 0 over here, and it's positive over here. So basically a local minima is happening in such a case. Now what is the third case? What can be the third case? Over here again we have defined a function fx, and f dash x equals to 0 for, let's say, x equals to c. So basically we have a function over here, and this point c is over here. Now there can be two cases. Let me draw two cases over here as well. So this is c, and this is also c. The first case would be it's negative over here, and it's also negative over here. It's positive over here, and it's also positive over here. How is that possible? So we have a curve of, let's say, this sort. So it's negative basically. So it's going like this. It becomes 0, and again starts going negative. In this case, it's going up. It becomes 0, and it's again going up. So basically at just one single point, it's becoming 0. Again over here, it's at just one single point, that is c, it's becoming 0. So when we have this kind of case, we cannot say that we have a local minima or local maxima. So basically this is the point of inflection. So where we have just f dash x equals to 0 at one single point, but the overall trend continues. So this is the trend of slope. So positive slope, negative slope, negative slope. It's continuing, but we have just one single point where f dash x equals to 0, right? So how do we define point of inflection? That was one of the property, but how do we define point of inflection? So point of inflection is a point where curvature of graph changes. So let's draw it more neatly. So this is a point where, f dash x equals to 0. It might not look like on the graph, but it's actually there over there. So this is the point where f dash x equals to 0. This is f dash c equals to 0, x equals to c, and f dash c equals to 0. So this, if we talk about this curvature, so it's concaving downwards. If we talk about this curvature, it's concaving upwards. So curvature has changed with from this particular point. So it was downwards earlier, then this point came, it's upwards now. So this is how we define point of inflection. Now let us discuss this particular example. Discuss the extremum of fx equals to 40 divided by 3x4 plus 8x cube minus 18x square plus 60. So basically we have got fx equals to 40 divided by 3x4 plus 8x cube minus 18x square plus 60, right? Now the first step would be to calculate the f dash x. So we'll be getting minus 40 times 1 by 3x4 plus 8x cube minus 18x square plus 60 raised power 2 multiplied by differentiation of this. So we'll be getting 12x cube plus 24x square minus 36x, right? So basically we are getting what we are getting over here. Let's take out 12 common from here. So minus 40 into 12 into x, and also we'll be getting x square plus 2x minus 3 divided by, let's call it as a square. So this is a square. So basically what we have got over here, 12 into 40 into minus x multiplied by x plus 3, and this is, yes, x plus 3 and x minus 1. divided by a square. So this we have to equate it to 0, right? Now let's try to plot the number line over here. This is x equals to 1, this is x equals to 0, and this is x equals to -3. But here we have a caveat over here. We have minus x over here. So basically whatever we are plotting with the help of wavy curve, it would get reversed. So we used to plot plus minus, but over here we'll be getting minus plus minus plus, right? So basically over here what is happening, if we try to plot the graph, we have a positive slope over here, we have a zero slope over here, we have a negative slope over here, we have a positive slope over here, we have a we have a negative slope over here, we have zero slope over here, and we have a positive slope over here. This is zero, and again this is negative. And this also makes sense, right? Because we have a quadratic biquadratic function in the denominator. So eventually if we go to infinity or minus infinity, this value should become close to zero. So basically this value should be minimized as much as possible if we go far away on both left and right hand side. So this also makes sense in that particular aspect. So we have got a point of local maxima over here, local minima over here, local maxima over here. If we talk about global maxima, global minima over here, we can clearly see that this function would eventually go to close to 0. If we put x equals to infinity over here, then this function would go to close to 0. So basically we'll be getting 0, close to 0 over here, close to 0 over here, unless we are getting a negative value over here. So we'll have to calculate that. If we're getting a negative value over here, if that is the case, then this is the local minima, a global minima. And if that is not the case, if that is some positive value, in that case this particular 0, close to 0 value is global minima. And for the case of global maxima, we have to compare these two local maximas over here. Whichever is the having maximum value, that is the global maxima. Now let's look at one more example. If x equals to ln x by x, and obviously x is greater than 0, and we have to find out the maxima and minima over here. So we have fx equals to ln x by x. So the first step is to calculate f dash x equals to, we'll have to use the quotient rule over here. So this is f, this is g. So f dash dot g, that would give me 1 by x dot x minus g dash dot f. So that would give me 1 dot ln x divided by x square. So that comes out to be 1 minus ln x divided by x square. So we have to equate this to 0. For that we'll be getting x equals to e as the point where either minima or maxima is happening. So let's try to plot it once. So basically this is our point x equals to e. So if I put e plus h over here, let's say this is e minus h and this is e plus h. If I put e plus h over here, so this becomes a little bigger than 1. So overall numerator becomes negative. So this is negative. And similarly, if I put e minus h over here, this becomes a little lesser than 1. So this overall numerator becomes positive. So this is positive. So we have something of this sort: positive slope, zero slope, and negative slope. And these two functions are, this particular function is obviously differentiable. There is not a case where this function is not differentiable in its domain. So this is the point of local maxima. Now if we talk about global maxima and global minima over here in this case, so basically we have fx equals to ln x by x. So we have domain from x belongs to 0 to infinity. So if we take x equals to 0 plus, so basically left extreme of this particular function domain, in that case we'll be getting fx equals to close to minus infinity, fx close to minus infinity, because ln x will become minus infinity and x is already very small, like 0 plus. So that would make fx as minus infinity. So minus infinity is the global minima over here. And if we talk about global minima, if we talk about global maxima over here, in that case this particular value is the global maxima, because if we move forward, x increases faster than ln x. If you apply the limit over here as well, you'll find out this will eventually become close to 0. So this is the case of global maxima over here. The local maxima is the global maxima, and global minima is minus infinity and not 0 over here, right? So with this particular question, we end the first order derivative test for differentiable functions. And in the next lecture, we'll be talking about second order derivative test. And after that, we'll be done with the OD series and we'll be starting with integrations. So let's meet tomorrow. Thanks for watching.